Hello, welcome to my channel. I hope you're doing well. So in this video I'm gonna derive the circuit response of RLC circuit, in this case the series RLC circuit, when the input excitation is a sinusoidal. So in my previous video thus far I have derived the the source free response of RC and RL circuit, then step response of the RC or RL circuit, then I had derived the sinusoidal response of the RC and RL circuit, and then I had derived the source free response of series RLC circuit. Then I had derived step response for the series RLC and parallel RLC circuit, both in cases for RL and RC also. And now what I'm gonna do is I'm gonna derive the sinusoidal response of the full RLC circuit, and I'm gonna also show you the parallel response, parallel RLC circuit response. So the series RLC and parallel RLC are duals of each other, electrical duals, so the equation will be somewhat similar. So if I get the response of the series RLC circuit, I will automatically be able to easily get the uh, circuit response of the parallel RLC circuit. So let's get started. So because this is the input excitation is the sinusoidal, let's say that, so the say the input is this Vs sin omega t. This is the excitation, so for which this is the voltage input, so for which the response should be current, which is it. So because this is a this is an LTI system, RC circuit is an LTI system, and R, L and C are linear elements, and L and C being the dynamic ones. So this will generate linear differential equation with constant coefficient. Let me um, derive those. So here I will assume, for sake of this, for sake of simplicity, that IO because initial current through the inductor is 0, and initial voltage across the capacitor is also 0. So because I have had used these initial current and voltage terms in my other videos, for this sinusoidal input I will assume that these two are 0 for simplicity, because it will make the equation, the derivation, bit complex and unnecessarily long. So by Kirchhoff's voltage law, we know that voltage across the resistor plus voltage across inductor plus voltage across capacitor is the inputs, which is V in, which is Vs sine omega t, Vs being the magnitude of the input excitation. So Vr is IR, so I being the current, the loop current, plus V is I, sorry, so VL, voltage across the inductor, is L, d by dt I, plus, so VC is integration 1 by C I dt equals to Vs sine omega t. So this is the equation, the differential equation with constant coefficient R, L and C being the constants. Now if I just rearrange this, and if I take the d by dt as, so say this is d by dt, and 1 by d is integration. So d is the linear differential operator. It will make our derivation easier. Okay, so I will be using d the linear differential operator, because the equation is linear, the system is linear, and it will make our lives more easier. So this will be I. So here I is the function of time. Okay, you have to obviously remember that. So IR plus L D I plus 1 by C D I equals to Vs sine omega t. Now if I take the common, so R plus LD plus 1 by CD IT equals to Vs sine omega t. So this is the equation. When rearranged, I will rearrange this further. So L by D out. So if I take L by D common, it will be like this: D squared plus R by LD plus 1 by LC IT Vs sine omega t. So now D square plus R by LD plus 1 by LC IT equals D by L Vs sine omega t. If I do this like D square plus R by LD plus 1 by LC IT equals, so this will give me Vs omega by L. D is differentiation, so cos omega t. So there's no doubt about it. So I have just done the differentiation. Okay, differentiation of sine omega t with respect to t is cos omega t, or omega cos omega t. So basic rules. So what I'm gonna do now is, so I'm gonna take this part out of the equation now. So cos omega t by d square plus r by l d plus 1 by lc. Now I'm gonna use this formula, which is this. So if I have 1 by fd, so remind you, in this case I am not interested in the transient response. Transient responses will be more or less the same as the previous source free response and the step response videos. So I'm interested in the particular integral. Okay, so the this formula is for mainly for particular integral. So if I have cos, say cos omega, say omega cos omega t, the this is a formula you can find in differential equation books. So it will give me cos omega t by f minus omega squared. So if the function has, in the denominator, the differential function has which differential function with d, the differential operator, if it has d squared term, so the function will become, the d square will become the function with minus omega square, omega being the uh, coefficient in the theta, with theta, so cos omega t. So it will give d square will be replaced by minus omega square. So this is a basic formula. I'm gonna use this. So Vs omega by L, so cos omega t by minus omega square plus r by l d plus 1 by LC. So I'm gonna take this 1 by C and replace it with omega n. Omega n is natural undamped frequency. If you haven't seen my previous videos, I have discussed about the natural undamped, so undamped natural frequency in details, so you can watch those first if you don't understand what I am doing here. So now what I'm gonna do is, so here, so V is omega by L. This is the magnitude, omega is the frequency, L is inductance. So cos omega t by, so I am taking r by L common, so d minus L by r omega square minus omega n squared. Okay, I hope you understand what I have done here. So this L and L will cut out and it will leave us with V is omega by r and cos omega t by cos omega t, this is cos omega t by d minus L by r omega minus omega n squared. So thus far we have found, thus far I have found that I am finding the particular integral ip. Okay, so omega by r, so omega by r cos omega t by d minus L by r omega minus omega n squared. So I want a d squared term in the denominator, so I will use uh, the uh, the algebraic formula a square minus b square. So for this I need d plus L by r omega minus omega n omega square square square. So I need this term, so d plus L by r omega square minus omega n squared. So now what I will have is ip, the particular integral or steady state response. Okay, we are interested in the steady state response for the sinusoidal input because it is of significant, so it is of significant importance. So this is, so v is the magnitude by r and it will be, so if I just multiply this with the cos t, it will be, so d is differentiation, so it will give me minus omega sine omega t plus L by r omega square minus omega n square cos omega t by d square and minus L square r squared omega square minus omega n square whole squared. So so my initial value, the numerator is cos omega t, so for that, or sine, doesn't matter, the d square term will be minus omega square. So if I take the ip and v is omega by r and minus omega sine omega t plus L by R. So omega minus omega squared minus omega n squared cos omega t by this is minus omega squared minus L square R squared omega minus omega squared minus omega n squared whole square. So this may look a little bit messy, but if you can understand this, so I have no differentiation, no differential operator, simply. So here I just have to rearrange this now. So if I take minus omega by r out, so it will give me minus omega by r. I have taken this as let's say common, so it will be r sine omega t, and this will be minus. So here what I am gonna do is I'm gonna take omega by L out from this, so it will give me, so omega L minus 1 by omega c. You can understand if you just ponder that what I have done here, it is very beautiful. So this is x, the LC part, the reactance part, and this is the resistance part. In the denominator also we can do this. So here is minus omega square by r square. If I take common, it will eventually give me r squared plus. So here also I will take omega by L common from this term, so it will give me omega L minus 1 by omega c whole squared. So our work is almost done, if you can see. So this will cut out, so this will cut, minus also cut out, this will cut out. Okay, so now what we're left with is the magnitude, nothing else, and I have r sine omega t minus x cos omega t by z, which is impedance square, the magnitude of the impedance. So here what I have done is that if z is in frequency domain, r plus jx, where x is omega L minus 1 by omega c, and if I take phi z equals to tan inverse x by r, then this will easily give me, so here's the magnitude and z cos omega t, because if this is z, so this will be r and this will be x, and this is phi, so this is phi, okay, phi z. So this is z cos phi z, which is R. R is the magnitude cos phi z, and X is Z sin phi z, if the uh, angle is phi z. So now what I'm getting is cos phi sine omega t minus xl x is the reactance is z sine phi z cos omega t by magnitude of the impedance of the RLC circuit whole squared, the magnitude of the impedance. Now, so I'm left with V. If I take the Z common, the magnitude common from the numerator, it will leave me with only Z, and I have, so I have sine omega t cos phi z minus cos omega t sin phi z, which will eventually give me Vs by z, and by trigonometric identity formula this will be sin omega t minus phi z. So this is the steady state response of the series RLC circuit to a sinusoidal input in time domain. So this is the time domain analysis. So I think you have understood it well. This is very easy and it's intuitive. So there will be a phase shift in the response, the current response, and so this is it, and this is very beautiful. So I have found the circuit response, which is current response. So I'm not writing the transient part. um, the transient part will be more or less this. So Vs by omega d, which is the damped natural frequency, the z part exponential sigma, this is the damping coefficient sine phi z, then more or less there will be a part like this with the main part, the particular integral steady state response. This is the steady state response. So I am gonna ditch this. So just because the steady state response is of importance here, so my main response, the derived response is this: Vs by z sine omega t. Omega is the input frequency minus phi z. So this is the response. So this is the steady state response. Steady state response of the series RLC circuit. So now I'm gonna derive the parallel RLC circuit response to sinusoidal excitation. So now I'm gonna derive the circuit response RLC. So I'm gonna derive the circuit response of this parallel RLC circuit. So for parallel RLC circuit, I'm gonna take a current source. So I'm gonna assume the current input is I in the magnitude sine omega t, and I'm also gonna assume initial current through the inductor is 0, through the capacitor initial voltage is also 0. I'm not gonna consider this. I'm just gonna consider this is sine omega t. And even for the input, the sinusoidal input, I'm gonna ignore the transient introduced by the input. So there are two types of transient: the inherent transient because of stored energy, and the transient introduced by the input. So I'm just interested in finding the particular integral from the linear differential equation with constant coefficient generated by this parallel RLC circuit. So by KCL, so KCL will give me IR plus IL plus IC. So this is I, which is is sine omega t, because the input at node, this is the node and this is reference node. So it will give me IR is V by R. V is the response. So if my input is or if my excitation is current source, current input, my response will be voltage. There's no doubt about it. So IL is, so 1 by L V dt plus IC is C d by dt. V equals to is sine omega t. So like earlier, I'm gonna take the differential operator. So it will give me V by R, C by D common. It will give me obviously D squared plus, if you look attentively for a few moments, you will see what I have done and you will understand. So if I take this, it will become CD this, and it will be, so 1 by R and dd, yes, this 1 by RV, yeah, this and this. So now what I'm gonna do is, so V is obviously function of time. So if I take is by C out and differentiation of sine omega dt by d square plus 1 by RC d plus 1 by LC. So D is differentiation. I am using this as an operator, which is D. So differentiation with respect to time will give me, so V, I'm taking the particular integral, not the transient response. So I is omega will come out by C, and I will find cos omega t, and because of this, by the formula of differential operator for particular integral problems, this square term in the denominator will become minus omega squared due to cos omega t or sin omega t. So the formula will be the same for both cos and sin. So this is minus omega squared plus 1 by RCD plus 1 by LC. So what I'm gonna do is the particular solution of the voltage response, which is is omega by C. I'm separating the magnitude parts, which is in part of the differential relation. So if I just rearrange this, it will give me, now I will directly get, so here CC will cut out, so it will give me 1 by omega C R, and I will have cos omega t by d minus RC omega square minus omega n squared. So to get, so if I want to, like, I wanna remove this d, so I have to get the d squared term like this. So I have to use d square d plus RC omega minus omega square minus omega n square to get the d squared term. I is omega r. Now is d plus RC omega square minus omega n squared in the brackets cos omega t by d square minus r square c squared omega square minus omega n square whole square. So now this will give me is omega r and minus omega sine omega t plus RC. So if I take omega by C out, so omega by C, omega L minus 1 by omega C cos omega t. Now this will be minus omega square, so minus omega square minus r square c square. If I take omega by C out from this also, it will give me omega square by C square omega L minus, sorry, omega C. I have done such a big mistake. So this will be omega C minus 1 by omega L. Okay, so you have to keep in mind for the parallel RLC circuit, the reactance part will change. So here this reactance is, this is not reactance, this is susceptance. You have to bear in mind that. So this is square whole squared. Now so I is omega r. So if I so this cut out. So if I take omega r from the numerator common, it will give me minus omega r. If I take, so omega r, it will give me so it will give me 1 by r sine omega t, then minus omega c minus 1 by omega L cos omega t. Then so from here, if I take omega minus omega square r squared common, it will give me 1 by r square plus omega c minus 1 by omega L whole squared. So I am finding the voltage response for the parallel RLC circuit So so far I have got this, so so this and this will cut out along with the minus sign. So what I am left with is is and sine omega t by r minus omega c minus 1 by omega l cos omega t by 1 by r square plus omega c minus 1 by omega l whole squared. So now for this parallel configuration, if I take the admittance, sorry, so this is magnitude. So if I take admittance as conductance plus susceptance, where conductance is 1 by r, susceptance is omega c minus 1 by omega l, and then the magnitude is g square plus b squared. The angle is tan inverse d by g. So this will give me, so this is basic phi. Oh, so let me write this phi y. Okay, admittance angle. So this is y, this is b, and this is g. So for the parallel RLC circuit, obviously, so this will give me voltage response, the particle integral or steady state part. I'm ignoring the transition response part because it is not that significant for this. You can derive it yourself. So this will give me is and g sine omega t minus b cos omega t by magnitude squared. Now is y squared, so y cos phi y sine omega t minus magnitude sine phi y cos omega t. So this will give me is by y, and by trigonometric formula it will give me sine omega t minus phi y. So this is the answer for the this is the response, the voltage response for the parallel RLC circuit. So I have now derived the full at least the main part, the steady state part of the parallel and series RLC circuit. I hope you have understood. So let me rewrite this. So our my main derivation is this: the steady state response, which is is by y sine omega t minus y. So there is a phase shift, and you can understand what I have done here. So this is the voltage response of the parallel RLC circuit. So in summary, the So in summary, the circuit response for the series RLC circuit for voltage excitation is the current, which is the, and the in steady state the current response is IT. Say this is the steady state response. I am interested in the steady state response. So IT should be and is the voltage magnitude, if it has any magnitude, the impedance, and the sinusoid part, sine omega t minus phi z. And for the parallel RLC circuit, the for the current input excitation, the circuit response will be voltage, and I am interested only in the steady state part. So VSS, say the steady state part, T, which is input magnitude, the magnitude of the excitation, admittance, sine omega, sine omega t minus phi y. So this is straightforward, and Z is R plus jx, where x is omega L minus 1 by omega c, and uh, phi, sorry, so magnitude of so zx can be written as in phasor form like this. So, and here admittance is G plus JB, conductance plus susceptance, where B is equal to omega C minus 1 by omega L. This can be written also as phasor form by Y. So the magnitude of impedance is R squared plus X squared, and phi Z is tan inverse X by R, and Y is G square plus B square. Phi Y is tan inverse D by G. So this is the circuit response of the series and parallel RLC circuit in time domain. Okay, so I have derived the steady state response of the two circuits in time domain. So I hope you have understood this explanation. If you have any problem in understanding my derivation, you can tell me. I will obviously try to explain in a more if there is any more intuitive and easier way, I will obviously try. We will discuss it. So thank you for watching this far. I hope you enjoyed this video.